Welcome to this particular module. So, in the last two modules what we have seen several sensors and its application, right, and today's module we will be focusing on few more sensors and then we will move to actuators. Okay. So, another application of a sensor is in microfluidics. Now, a fluidic system is where the fluid can flow, right. When you make a micro channels of micron dimensions, it becomes a microfluidic channels, right. Now, how can you use the microfluidic system for, let us say, drug screening? What do you mean by drug screening? If you are given 7 different drugs, which drug will be effective for a particular patient? How would you know? You don't know, right. So, can we come with an engineering solution so as to find a drug for that particular patient? So, out of 7 drugs, this drug you give it to this particular patient, let us say drug number 3, while drug number 5 you give to the next patient, because that patient's body is more the drug number 5 is more has a more efficacy for that patient's body compared to the first patient where drug number 3 was having more efficacy. Efficacy is more effective. Okay. So, how we will screen the drug, which drug to take, screening of drugs, right, that is our idea and that is where our sensors will come into picture. So, if you see the screen, what you see here is a microfluidic chip for rapid drug screening, and here you see is let me first make you understand how the current scenario is, that from the time the patient goes to the hospital there is a consultation. So, we talk about here, let us say we keep our focus on breast cancer, because like I said, breast cancer is the second largest cause of cancer related death in women. Okay. So, we focus on breast cancer. So, when a woman goes to a hospital and there is a consultation in the screening which is called mammography, right. So, from the mammography it is found that there is a suspected region, then the person has to go for a consultation and there is a recommendation for biopsy. Biopsy is taking out the tissue from the body using a needle, using a biopsy needle, alright. And then after taking the biopsy tissue, there are some PET lab tests are performed to understand whether the tissue is cancerous or not. Now, what we want to do? For this particular tissue, we want to take the tissue and we want to mince the tissue, and then further we will overnight digestion with collagenase, and this collagenase is used to digest the tissue and to form the tumor organoids, and this tumor organoids we can do trypsinization and form single cells. So, do not worry about this whole procedure, I am just showing it to you, right, nothing to worry about. And once you have single cells, you can also use a chip to understand the cell properties and the impedance of the cell. Okay. So, before we go to this particular test, let us see this example. So, we will understand it better. So, once you have this sample, you see the sample, you load the sample in a 1.5 ml tube, and then 20 microliter of the sample you place on this particular chip. This chip is a impedance sensor. So, what I mean by impedance sensor is there are interdigitated electrodes like this, okay, and then there is a contact pad, another contact pad. So, if there is a well like this, there is a well which you can see here, right. I will put cells on this particular chip with some material. What will happen initially when there were no cells, my impedance is infinite. When there are some cells, I will have some impedance. Let us say I have 100 kilo ohm impedance value, alright, Z equals to 100 kilo ohms, here Z equals to infinity when there are no cells. When I place the cells, my Z becomes 100 kilo ohm. Now, if I load a drug on this, if I load drug 1, right, what will happen? What is the role of a drug? The role of a drug is to kill the cells. So, if the drug is effective and if the cells dies, what will happen? There will be change in the impedance value. Why there will be change in impedance value? Because the conductivity will change, because the dying or lysing of cell will cause the constituents within the cell to come out, and those constituents will increase the conductivity, resulting in decrease in the impedance. Got it? So, if I can have 8 of such wells with an interdigitated electrodes and I place different drugs and I see which drug is effective based on how much is the impedance change, I can say that the drug which is more effective would have, the chip on which the drug we have loaded is more effective would have more impedance change compared to the chip which the drug is not that effective. So, that effectivity or the efficacy of the drug we can design or we can determine with the help of a sensor. Where is our sensor here? Our sensor here is an interdigitated electrode within an SU8 well or any well. You got it? We will see as a part of this course how to design and fabricate such sensor. Now, you see the screen. Okay. So, what I am saying is, let us take 4 different drugs, okay, just for an example. You can take 7, you can take 8, you can take 100. Of course, there are no 100 drugs that to try, but I am just saying. So, let us say this is A, B, C and D. Right, 4 different chips, interdigitated electrodes, right, 4 chips were interdigitated electrodes. Contact pads, right, where you can measure impedance. ZA, ZB, ZC, ZD, all right, and you have a well, so that the cells would not come out of the well. You have a well, so cells would not come out of the well, all right. Now, what I said, you load the cells. So, understand, when there is cancer, it is always surrounded by ECM. ECM stands for extra cellular matrix. When there is cancer, it is always surrounded by extracellular matrix. So, from where we can get extracellular matrix in our case? In our case, our extracellular matrix is matrigel. So, we will load these cells plus matrigel. Okay. So, the question would be, what if this is a cancer, this is ECM, your question should be, what is the role of ECM? The role of ECM in the case of cancer is to provide nutritions to the cancerous cells, all right. So, the nutritions are formed or are given to the cells through the extracellular matrix, all right. Now, this is a in vivo condition. You have to understand 3 different terms. One is in vivo or in vivo, ex vivo or ex vivo, and in vitro, all right, 3 terms. In vivo is inside the body. If I it's funny drawing, isn't it? But assume that this is a rat, you have to assume. Okay. Now, if I do experiments in the rat, if I load the cells in the rat's body, cancer cells, and I study what is going on within the body, it is a in vivo study. If I take out the tissue, if there is a tumor here, if I take out this tumor, right, from the rat, it is ex vivo study. But if I replicate this same tumor on a platform in the lab, it is a in vitro study. You got it? So, in vivo, ex vivo and in vitro, 3 terms that you need to understand with my funny picture of a rat, which you do not have to worry about. ZA, rat is deleted, ZB and ZC. All right. So, now if I load these cells with matrigel and here also I load cells plus matrigel, here also I load cells plus matrigel, and in the 4th chip also I load cells plus matrigel. All right. So, let us say these are cells with matrigel, cells with matrigel and cells with matrigel. Now, what did I say? Add different drugs. So, there are 4 drugs D1, D2, D3 and D4, right. These cells are from the same patient, all right, cells are from the same patient, and assuming that these cells are cancerous cells, CANCEROUS, cancerous cells, all right, assuming these are all cancer cells. Now, if I load drug 1 here, drug 1, I load drug 2, I load drug 3 and on drug 4 I will load in the chip number D, right. Now, I will see ZA1, ZB1, ZC1 and ZD1, right. That is a change in the impedance value when I have loaded the drug. When I load the drug, there will be change in the impedance value. The impedance change which is maximum from its base impedance. So, the change in impedance from its base impedance is maximum. That drug I had to give to that particular patient, because that drug is more effective. You got it? That is what I said. But there is a catch. What is the catch? That now the drug is in continuous contact with cells and matrigel. Drug is in continuous contact with cells and matrigel. Then how can we use this drug? How we will rely on this data? Because now what you are talking about is that if I have some kind of problem in my body, let us say there is a cancerous tissue in the body and I have been given a drug, then do you think the drug will go and stay in the same area? It will not. Why? Because the body is not static, it is dynamic. The blood flows, the drug will flow in the blood and blood flows in the body, and this is a dynamic system. But what we are talking about in the wells are all the static systems, right. Thus, the results that we obtain from the static system, we may not rely completely on those results. You got it? That is a difference. We have to understand how a dynamic system would work, all right, and that is why we will design a microfluidic chip. Okay. So, if you come back to this particular design, now I have this same interdigitated electrodes, right, but I have a channel like this and connected like this. Right. So, let me just remove this guys, so that you do not get confused. Okay. What I have drawn is there are two channels, you can see one small channel and one big channel, right, one small channel and one big channel, and in the smaller channel there are interdigitated electrodes, correct. There are interdigitated electrodes. This is your impedance measurement Z. These are interdigitated electrodes. This is a smaller channel. This channel is used to load cells with matrigel. Right. So, everywhere there are cells like this, cells are there. Now, I will pass the drug through. So, everywhere there is matrigel and cells. Okay. I will pass the drug through this channel continuously. So, drug will pass continuously through this channel. When the drug passes through this channel, the drug will also infuse or diffuse into the smaller channel where there is a matrigel plus cells are there, right. This diffusion can be controlled with the help of a flow rate. So, this flow rate can be designed such a way that to mimic the diffusion of the drug inside the body. All right. So, this chip that we have designed, this is a microfluidic chip. The rectangle that I have shown is called microfluidic chip. Now, what will happen if my drug is effective, the cells in the smaller channel will start dying, and the death would result in increase in the conductivity and decrease in the impedance, is not it. I can develop 4 of these microfluidic channels and compare the results. This is my static platform, this is my dynamic platform. You got it. So, this is dynamic platform, this is static platform. Here I can see the change in impedance when there is a drug killing a cells. Here also in the static platform also I can see the change in the impedance when the drug is effective. But the dynamic platform is which is close to the in vivo situation inside the body, right. Thus, we can mimic the in vivo situation onto the in vitro platform by designing a microfluidic chip with an electrical sensor which is our impedance sensor, and that impedance sensor can be designed using interdigitated electrodes. Got it guys? Easy. I will help you to understand how to design and fabricate this particular electrode. Right now, just focus on that. Now, another thing that I have discussed is that the cells should be alive at 37 degree centigrade. We require 37 degree centigrade temperature to keep the cells alive, right. That is why you require a heater. So, now we have this is called mask. I will tell you what exactly mask means. This is mask number 1. Actually, this is actually mask number 1. this is mask number 2 and this is mask number 3. This is a separate mask for creating a molds, and you will see how can you design a microfluidic chip, right, for understanding the which drug is effective, and these are interdigitated electrodes. If I zoom this one, it will look like this. A further zoom in, looks like ohm symbol, right, it looks like an ohm symbol. And these are microfluidic channels, you can see small channel and larger channel. We will see, okay, in detail when we talk about fabrication. All right. Now, I will come to a next sensor which is used to understand the rapid antibiotic susceptibility. Now, what exactly rapid antibiotic susceptibility is there? You understand this thing. There is something called bacterial infection. Bacterial infection, and we can kill the bacteria with the help of antibiotic or antibiotics. Antibiotics are nothing but drugs, all right. Now, recently this bacteria started showing resistant to the antibiotics. That means, if a person has a bacterial infection, if we give antibiotic which is a drug to kill the bacteria are resistant to this antibiotic. So, how the person can be cured? Person cannot be cured, right. So, which antibiotic the bacteria is resistant, in which antibiotic the bacteria is susceptible, we need to understand. How can we understand? First of all, we need to understand to capture the bacteria from a sample. Secondly, to understand whether the bacteria is resistant to the antibiotic or not. For that, we will see how to design a sensor for a rapid bacterial resistance measurement or antibiotic susceptibility measurement called AST, antibiotic susceptibility measurement, the testing, all right. So, these are two different platforms. We will discuss this thing in detail in our class, and this is also on the sensor design, all right. So, let us finish the today's module on this particular note. I will discuss in detail the 3 more sensors which are one related to combinational therapy, one related to flexible sensor, one related to electronic nose, one related to immunotherapy, and then we move to and I will show you a very beautiful image of a fly that we tried to measure the weight, and followed by the actuators, right, and then we will start understanding how to design the process flow for fabricating sensors, all right. So, till then you take care, I will see you in the next module.